A compiler can feel a lot like a magic trick, right? You feed it your code, this stuff we can actually read and write, and poof, out comes a program the machine can understand. But it's not magic. It's actually a super organized process. And today, we're going to crack open that black box and show you the elegant assembly line inside that makes it all happen.
So, what is a compiler at its absolute core? Well, it's a translator. That's really it. It's this vital bridge between our world, the world of languages like C++ or Python that we can understand, and the machine's world, which is just a stream of ones and zeros. It's the tool that takes our logic, our ideas, and turns them into something a computer can actually do. Okay, so here's our roadmap. First, we'll get the big picture of the compiler as this code translator. Then, we're diving deep into its two main halves, the front end, which is all about analysis, and the back end, where the new program actually gets built. And to finish it all off, we'll talk about why this whole structure is honestly a game changer.
All right, first up, let's get that bird's eye view. We need to see just how a compiler manages to bridge that massive gap between the code we write and what the machine actually understands.
And here it is. This is our assembly line. Just imagine your source code getting fed into the top, and at the very bottom, out pops the final program that the machine can run. Every single step you see here is a distinct phase. It takes the output from the phase before it, does its own little job, refines it, and then passes it right down the line. It's a really elegant and, believe it or not, super modular system.
Now, this two-part structure, this is the real secret sauce of modern compilers. One source even calls it a wise compromise. You've got the front end, which handles all the analysis. Its whole job is to figure out what your code actually means. And here's the key. It doesn't care one bit what kind of computer it's running on. Then you have the back end. It's all about synthesis. It takes that understanding from the front end and gets to work building the final program for a very specific target. Like an Intel chip, or maybe the ARM processor inside your phone. So let's start with that first half of the assembly line, the front end. Let's really dig into how a compiler starts to make sense of our code. This whole analysis journey basically happens in 3 steps. You can think of it like this. First, the compiler has to learn the individual words. Then, it checks the grammar. And finally, it has to make sure the sentences you've built actually mean something coherent. Okay, first stop, lexical analysis. The best way to think about this is like a scanner for your code. It just plows through everything, character by character, and groups them into meaningful little chunks we call tokens. So in this line of code here, the word initial becomes a token. That plus sign, that's a token. Even the number 60 becomes its own token. What comes out the other side is just a simple stream of these words, ready for the next phase.
Next up, we have syntax analysis, which you'll also hear called parsing. This is basically the grammar check. It takes that stream of tokens we just made and asks a simple question. Do these words form a valid sentence based on the rules of this programming language? And if the answer is yes, it builds this awesome structure called an abstract syntax tree, or AST. Seriously, it's like a family tree for your code. It shows the exact relationships between all the different pieces.
All right, so our code is grammatically correct, but does it actually make sense? That is the job of semantic analysis. This is where the compiler does all the critical thinking. It's checking for things like, hey, are you trying to add a number to someone's name here? Because you can't do that. Or maybe you're using a variable you never even defined. This phase makes sure your program is logically consistent.
Okay, so with the analysis phase complete, the front end has done its job. It hands off this verified, perfectly structured representation of our code. Now the baton is passed to the back end, and its job, synthesis, or actually building the target program, can finally begin. And hey, guess what? The back end also has 3 main steps. It starts by creating a generic version of the program. Then it spends some time polishing it up to make it better, and then finally, it does the last translation for the specific target machine. First up, the compiler creates something called an intermediate representation, or IR. Think of this as a generic, really simplified version of your program. It's not tied to any specific processor yet. A really common format for this is called 3-address code, where every single instruction is broken down into a super simple step with at most 3 parts. And why do this? Well, this super simple format makes it way easier for the compiler to analyze and, importantly, improve the code in the next phase. And that brings us to code optimization. This is a hugely important step where the compiler basically becomes a meticulous editor. It pores over that intermediate code and is constantly looking for ways to make the final program run faster or use less memory. It might spot a calculation you're doing twice and just do it once, or maybe it'll rearrange some instructions for better performance.
And the whole time, it's making these changes without ever altering what the program actually does. And just to give you a sense of how deep this rabbit hole can go, there was an early compiler for a language called PL/I that was famous for having, get this, 70 different optimization passes. 70. Every single pass was just another chance to comb through the code and try to make it a tiny bit better.
And finally, we've reached the finish line. Code generation. This is it, the last step on the assembly line. The compiler takes that beautiful, optimized intermediate code and translates it into the native language of the target processor. It swaps out all those generic instructions for the very specific ones that this particular CPU will actually understand.
Now, throughout that whole journey, from the very first step to the very last, there are two key components that are always working in the background. If you look at our assembly line diagram again, you'll see them hanging out on the side, the symbol table and the error handler. You can think of them as the supervisors for the whole operation.
So the symbol table, it's pretty much the compiler's memory. It's this big data structure, kind of like a dictionary, and its job is to keep track of every single variable name, function name, or any other identifier you've created in your code. It stores all their important info, like their types, so that any phase in the assembly line can quickly look them up and make sure they're being used correctly.
And then, of course, you've got the error handler. We've all seen its work, right? Its job is to spot and report any mistakes it finds along the way. Doesn't matter if it's a simple typo found in the lexical phase or a more complex type mismatch from the semantic phase. And you know, the really good error handlers don't just give up at the first mistake. They use clever recovery strategies. There's even one called panic mode, where they'll skip a bit of problematic code to find the next good spot. That way, they can keep compiling and report a bunch of errors to you all at once.
Okay, so we've walked through the entire assembly line, we've seen all the parts. But that brings up a really important question. Why? Why is it structured exactly this way, with this very specific split between the front end and the back end? Well, the answer is actually incredibly powerful.
Really, it all boils down to one word: portability. By separating the front end, which only cares about the programming language, from the back end, which only cares about the target machine, you can do something truly amazing. You can write one single front end for a language like C++, and then you can just plug in different back ends to make programs for Intel chips, or for the ARM chips in our phones, or for pretty much any other computer architecture out there. This mix and match approach is the fundamental reason a single programming language can run just about anywhere today.
You know, there's a quote from our source material that just nails this. It says the advantage of this whole separation is, quote, inestimable. And honestly, that is not an exaggeration. This specific design choice is what allows modern software to be written one time and then run almost everywhere. A truly fundamental idea that we kind of just take for granted now.
So there you have it. A compiler isn't some magical black box after all. It's this elegant assembly line, a really structured process that's been refined over decades of work. And understanding that structure, I think, leaves us with a pretty fascinating question to ponder. As our computers and our programming languages keep evolving, how is this fundamental design, this assembly line, going to have to evolve right along with them?